Hi everyone, my name is Alyssa Livinggood, and my presentation today is going to be on smart inverters. During this presentation, there are a few things that I hope to accomplish. First, I want to explain the working principle of a regular inverter before we go into what a smart inverter is and how that differs from a traditional inverter. And then I want to analyze why we use smart inverters and provide an example of a commercially available smart inverter. Before I start discussing what a smart inverter is, I wanted to make sure that everyone was on the same page about what a traditional inverter is. So we're going to talk about how it works and what exactly it does. So a traditional inverter converts a DC signal to an AC signal by approximating a sine wave. Here at the bottom of the slide I have a black box representation of that. On the left here you can see an example of a DC current signal. It goes in as just a constant signal over time. Once it goes through the inverter, the output is an alternating current that you can see here in the top of this figure to the right. So the question is, now that we have this black box representation, how does the inverter actually convert that DC signal to an AC signal? One of the fundamental concepts for understanding electricity is that current flows from the positive terminal of a DC voltage source to the negative terminal of that source. If the positive terminal of the voltage source is connected to the positive terminal of the load, then the load experiences a current flowing in the positive direction. However, if the negative terminal of a DC voltage source is connected to the positive terminal of the load will then experience a current that appears to be flowing in the negative direction. If you were able to manually switch the polarity of the DC source quickly enough, you would see a current that has a different amplitude over time. This is the definition of an alternating current. This idea of quickly changing which DC terminal the positive side of the load is connected to is how an inverter converts direct current to alternating current. An inverter is able to accomplish this using complementary pairs of electronic switches such as IGBTs or MOSFETs, which can quickly switch several times per second. Pulse width modulation, or PWM, is used to control how quickly the switches open and close. Controlling how quickly each switch opens and closes controls which side of the DC source the load is connected to and how long it is connected. This is how an inverter changes the direction of current to convert direct current to alternating current. I'll give a small example of this using the inverter topology shown to the right. The switches in this topology are IGBTs represented by S1 through 6. S1 and S3 are controlled by the same signal, shown in green in the bottom figure. S2 and S4 are controlled by the inverted value of this green signal. S5 and S6 are complementary switches controlled by the higher frequency blue signal in the bottom figure. When S1, S3, and S5 are on, the load is connected to the positive side of the DC voltage source, and it appears that positive current flows from the positive side to the load. When S2, S4, and S6 are on, the load is connected to the negative side of the DC voltage source and receives negative current. When S1, S3, and S6 are on, or conversely, when S2, S4, and S5 are on, the load is connected to the neutral point and no current flows. This output creates a quasi-sinusoidal wave, which can be filtered using capacitors or stepped up to higher voltages using a transformer. Now that we've talked about regular inverters, we can move on to talking about smart inverters. A smart inverter still retains all the functionality of a normal inverter. Its basic function is still to convert DC signals to AC signals. It's deemed a smart inverter when it has added capabilities. Those capabilities include monitoring and regulating the output voltage and frequency, and it also provides added protection against faults in the system that it's connected to. These capabilities are important when we start talking about why we need smart inverters in our evolving grid. With all of this background information, we can now answer the big question, which is, why do we need smart inverters? Traditional generation sources, such as coal, natural gas, and hydroelectricity, don't require inverters. When they produce electricity, they turn a turbine, which turns a mechanical shaft, which produces alternating current automatically. However, renewable sources, like wind and solar, produce direct current. Therefore, with the increased use of these renewable energy sources to connect them to the grid, we need to use inverters to convert the DC current that they produce to alternating current. This increased use of renewable energy sources is not limited to utilities. Now, private companies and residential customers can order solar panels to generate electricity at their factory, office, or home. This distribution of energy sources throughout the distribution system is one aspect of the emerging smart grid. The current distribution system was designed to be a radial system, meaning power only flows from the utility to the customer. Technological innovations are needed to ensure that these new distributed generators can be incorporated into the grid without affecting the power quality. Traditional electromechanical generation methods implement load frequency controllers to regulate their power output. However, since generation sources like solar and wind do not produce electricity electromechanically, a different control scheme is needed to avoid fluctuations in the voltage and frequency of the power in the grid. This is where the added capabilities of the smart inverter come into play. The smart inverter takes on the same role as the load frequency controller. Additionally, the smart inverter fixes an issue that has caused renewable energy sources to be a detriment to the power industry. Faults happen in the grid, and most are only temporary. However, when a traditional inverter experiences fluctuations due to faults, it severs itself from the grid. By doing this, generation is removed from the system, causing a further imbalance. This can have a cascading effect that causes more inverters to sever themselves and could lead to a blackout. The added capabilities of a smart inverter help it to weather these small temporary faults. Instead of contributing to the problem, smart inverters allow renewables to be part of the solution. This slide shows a picture of a utility-scale smart inverter attached to an array of solar panels. This particular smart inverter was manufactured by the company Huawei. Huawei manufactures smart inverters for both commercial and residential customers. Huawei is not the only company that manufactures smart inverters. Companies such as Enphase and SMA Solar also produce smart inverters. The market for such technologies is sure to grow as renewable energy sources become more common and regulations are put in place to promote the use of smart inverters. To recap, in this presentation, we have discussed the working principle of a smart inverter. In addition to converting direct current to alternating current, a smart inverter has the added capability of monitoring the voltage and frequency of the power in the grid. In this way, the smart inverter acts like a traditional load frequency controller. Not only does a smart inverter help ensure power quality, it also provides the system with added resiliency to faults. Finally, we saw an example of a commercially available smart inverter from Huawei. The market that is being targeted by Huawei and other companies will continue to grow. This prediction is supported by the graph below. Therefore, smart inverters will become a commonplace aspect of the grid as renewable energy sources become more prevalent and generation is distributed throughout the distribution system. Today, I was only able to give a brief overview of inverters and smart inverters. So if you all have further questions or wanted to do further reading, I've provided you here with the list of references that I've used. Thank you.